Okay, so what we see on this map is the mean daily river discharge, an average for a period from 1979 to 2018 from the ERA5 reanalysis data. And this is a modeled map. So what we see here is not a satellite image of where the rivers are, but it's modeled. And then we see where the water is. So basically it shows the main rivers in the world. But when we look at world water use, we see a graph that's very similar to other graphs that we see. Everything is always going up. Energy use is going up, electricity use is going up, land use is going up, but then also world water use is going up. And between 1900 and 2000, we see an enormous increase of freshwater use. These are data from FAO, Ecostat, a huge database of water withdrawal, water use. What we also see is where the water is used for. So the increase is mainly in agriculture, so water for irrigation. Industry is also going up, and then if we think of the functions of water, then this is mainly for electricity generation, but also when we produce products, this requires more water. For example, Coca-Cola. Municipal water is going up, so tap water supply for households, and the reservoir losses are going up, and this has to do with hydropower. If we look at the water supply system, so the freshwater system, what we see then is that we have basically the water resources, rain, so the precipitation that falls down. We can take water from surface water, so the rivers and the lakes, just as I just showed for the Mekong. We can take it from groundwater, and another source might be, if we don't care about the quality, is seawater. You can use seawater directly for the cooling of the power plants. If you are a country close to the sea, then you very often see that the plants are located near the coast. If you want to use it for the freshwater supply, then it needs to be desalinated. Then there's a trade-off for energy, because this requires a lot of energy. So this freshwater, if we look at freshwater alone, it's withdrawn as an inlet, and then depending on the quality that people want, it needs to be purified. So there is a pre-treatment before it can be supplied to households. It needs to be distributed in pipe system distribution systems, and then finally it comes to the user. Now here, between distribution, the overall distribution system, and the use, very often there are many leakages, so the efficiency can be quite poor. After use, preferably it goes to a wastewater treatment plant, but this is not always the case in developing countries. It is in developed countries. Then it is disposed again to freshwater system, and the circle can start again. So we need this water to produce goods and services. And when we look at our globe, we see a blue globe. This is seen from a satellite image in space. But we need it to produce lots of things. there is a division between the production of the water intensive goods and the consumption of water intensive goods. It is not so that the goods that are produced somewhere are also consumed at the same place as where they are produced. And this means that there is a gap between the production location and the consumption location. And here the trade comes in, because it can be so that in the areas where a lot of consumption is needed, for example, here in the developed countries, also the water is there for the production. As we have seen for the country Mali, where they produce gold and sugar, the gold and the sugar is not consumed in Mali itself, it's exported. So what you then see is that water is also a global resource. If we consume goods, for example, if we have something made of gold, or if we consume sugar that's made of sugar cane, we indirectly contribute to water depletion and pollution elsewhere. This also means that countries that have lots of water have other opportunities than water scarce regions. In the Middle East, for example, or in Northern African countries where water is scarce, there are other options than in water abundant countries. This also means that when you have huge trade flows over the globe, that countries become more dependent on other countries. They become dependent on the water resources that are elsewhere. Without those production constraints, it's not possible to produce gold or sugar. So this also means that water becomes a geopolitical resource. And it also means that we need to harmonize national water and trade policies. Yeah, can be seen from a global perspective. And what is then relevant is to quantify your water use, and a water footprint was developed to do this. What it does is that it tries to make a link between consumption in one place and impacts on water systems elsewhere. I mentioned the example of gold and sugar from Mali. And this means that consumption and production locations are not the same anymore. And what we see here is it's a very impressive photo made by Gleich in 1992, but it's still relevant. This is the Aral Sea in Asia. It shrinks. It still shrinks. It was much larger in the last century, but the sea is fed by rivers. The rivers are pumped dry for irrigation water for cotton fields in the area. It's a cotton producing area, so this also means that when we wear cotton and a cotton shirt, for example, coming from this area, we contribute to the situation of the Aral Sea. So if you look at the product, for example, sugar or sugar cane, then the concept of virtual water means that we do not look at the water that is embodied in the product, but we look at the virtual sense of water consumption. It refers to water that is needed for the production of a specific product. And when you start trading, for example, your gold and your sugar, then you trade virtual water. You bring water from one place to the other, not in the real sense, but in the virtual sense. For a water footprint assessment, we look at the volume of fresh water used to produce the product, and we sum it over the various steps of the production chain. So water footprint is the same as virtual water, but the problem with water is that it includes a temporal and a spatial dimension. It's important where and when the water was used. This water footprint concept has three components. We have blue water, green water, and gray water. I'll explain it here. Green water is basically the precipitation, so the water that's coming down in the form of snow or rain. Blue water is water from our surface water or groundwater. So green water and blue water together are the water consumption components. And then we include a third color of water, which is the gray water footprint. And the gray water footprint is defined as the water that you need theoretically to dilute the water to accepted water quality standards. But I say theoretically because gray water footprint gives an indication of how polluted your water is. When you want to make an assessment of a water footprint, then it requires the analysis of the full production chain. So you need to know where your products are coming from. And this is an example for an agriculture product, could be the sugar from Mali. It's produced by a farmer somewhere. There is green and blue water needed to produce this product. And there is also a gray water footprint because the farmer uses fertilizers and pesticides that are released to the soil. So you need theoretically a volume of water to take this in, to assimilate the pollutants. The products are sold to a food processor, so there's a virtual water flow from the farmer to the food processor. For example, you bring your sugar cane to a sugar processing plant. Here they also need some water to produce the sugar, maybe some blue water. And also there is a pollution here. So also a gray water footprint is generated. Then the sugar goes to a retailer, to a shop. Maybe also some blue water used for cleaning of the shop itself. It could be some pollution occurring there. And finally, the sugar arrives at the consumer. And here also some blue water is used, maybe for the cleaning of the cups, where they put the sugar in, maybe for the coffee or the tea, and also the consumer pollutes the water. Then it is very important to realize that we need to know how a product is produced from the farmer to the producer. Here we see an example of cotton. So the cotton is produced somewhere, it's harvested. But then we see that there are more products from a cotton plant. We have cotton seed and we have cotton lint. And the cotton seed generates cotton seed cake and cotton linters. And here the cotton also generates different products and finally ends up in a shirt. We then make an assessment of water footprint for the separate products, for the cotton seed, the cake, the linters, the final textile. And we do that according to an economic allocation module, where we allocate based on the value in money of the final products. When we make an assessment of the virtual water content of products, for example, for a crop, we have to look at the crop water use, so in cubic meters per hectare, and we express that per unit of yield, so in cubic meters finally per ton of product. We have to make an assessment of the water needed for the feed, and then add the drinking and servicing water. And then, as I mentioned before, you have to allocate over the root products and its derived products. If we want to make an assessment of crop water requirements, then we need to calculate the crop evapotranspiration, so the water that is evaporated from your crop and your soil. We quite often use then the Penman-Martin's equation. We need to calculate the crop evapotranspiration in millimeters per day, depending on the crop. So not every crop has the same crop evapotranspiration. It depends whether you grow maize or sugarcane. And it depends on the stage, the growing stage of your crop. In the beginning, when the crop is small, evapotranspiration is smaller, and it goes to a maximum and goes down again. And then we accumulate, we integrate the crop water requirements over the complete growing period of your crop. Irrigation requirement is very often modeled based on crop water requirements minus effective rainfall, and then you generate your irrigation requirements and your crop water use. How we make an assessment for cotton and what the consequences of cotton production can be in a specific area, and the example of the Aral Sea. We then arrive at a global average of 2,500 liters of water for one cotton shirt. So you can make this inventory using data from the Aral Sea and make the inventory for a cotton shirt. And this is a global average. We made a database for all agricultural products per country and even per province in a country. There's a huge database, and that's available on the website of the Water Footprint Network, where you can derive all the data for a specific agriculture product. So then you can make the calculations yourself, and you can also see the differences. Made assessment for all the large global traded commodities, organic, not organic, from animal sources, from vegetal sources. What we see here is a global average for wheat, rice, milk, cheese, pork, and beef. And it immediately gives an impression that there is a huge difference between the animal foods, for example, beef, or the crops, for example, wheat. And the animal foods have far larger water footprints, and this, of course, has to do with the feed ingredients, that an animal is not so efficient in converting a crop into an animal product. We can also see that there are huge differences among the products in a specific category. There's a huge difference between 1 kilogram of pork and 1 kilogram of beef. A kilogram of pork requires 5 cubic meters of water, and a kilogram of beef 15. And this also has to do with the efficiency of conversion. Yeah. That the cow is not so efficient in the conversion of its feed into the final product. This also has to do with the lifetime of a cow. In general, a cow goes to the slaughter, say, after 6 years, while a pig goes to the slaughter, say, after 9 months. So the cow needs far more feed during its lifetime and also then more water. Then we see the milk and the cheese. These are final products from a production chains. They are co-products together with the beef, and then it depends on how you allocate your water over the final products. When we go to the difference between wheat and rice, we see that rice requires far more water than wheat. And this also has to do, and I showed an example for the Mekong Delta, that rice is often grown in water, so it needs lots of irrigation water, far more than wheat. So this very well shows the differences among the products. Then you can calculate how much water you need, for example, for a slice of bread. Or you can calculate how much water you need for a kilogram of sugar, or for an egg, or for a product like hamburger, or for a tiny cup of coffee that you need 140 liters of water, or for chocolate. But also paper requires water. We also made assessments for energy, and there was already a question of water for energy. Also here we see huge differences between the energy carriers. We have a cluster of non-renewables and renewables. The cluster of the non-renewable energy carriers have far smaller water footprints than some of the renewables. So this means that if there's a shift towards renewable energy sources, then it matters a lot which one you take. For example, if you shift from non-renewable fossil fuels like natural gas, coal, or oil to hydropower, then it matters a lot where you put your hydropower, because in general the average water footprint is far larger than for the fossil fuels. We also saw that the shift towards biomass energy generates lots of water demands. So this is something you need to take into consideration when promoting energy transitions. With all those calculated data on foods, on electricity, on energy, we can also calculate the water footprint of the nation, of a country, for a consumer. We did that for countries in the world. What we see here are the water footprints in cubic meters per person per year. And what we see is huge differences. As I mentioned before, you can combine data on consumption per capita with information on specific water footprints for products. Now, there are two ways that water footprints can be quite large. Either your consumption is very large and you use lots of products that have huge water footprints, for example, lots of cotton or lots of meat, like they do in the United States and in many countries here in Western Europe. Or it can be, and we also see in Africa that there are countries with very large water footprints. It can also be that your consumption is very low, but that you use your water very inefficiently, so that the water footprints per unit of product are very large. And this is very often the case in these African countries. And it can, of course, be a combination of both. Here we see some examples of water footprints per capita with different clusters. So domestic water consumption, industrial goods, and agricultural goods. We see on the right-hand side, we see the United States, which has the largest water footprint per capita. But then we also see on the right-hand side, we see a country like Thailand and Nigeria. They also have relatively large water footprint, but this does not have to do with large consumption of goods, but it has to do with very poor agricultural situations, so that their yields are low. So they use the water inefficiently, generating large water footprints per capita. So for the United States, they do have an efficient agriculture system. You could think of decreasing their meat consumption, but for Nigeria and Thailand, decreasing consumption is not a good option because consumption is already low. But then it's better to focus on their agricultural system and make this more water efficient. If we look at the global water footprint and the contribution per consumption category, as I mentioned already in my first slide, that most of the water is related to agriculture. We also see that related to consumption. It's the agricultural goods that dominate the water footprint. A small part is used for industrial goods and some for domestic water consumption. So domestic water consumption is not always a problem. It's only a minor part of the global water footprint, and if there's enough money, then it should be possible to supply sufficient, good quality drinking water. So to repeat, what are the main components of a water footprint? It depends on consumption, and it depends on production circumstances. So the consumption characteristics, how much you consume of what, and your consumption pattern. So if you have a consumption pattern with a lot of electricity, with a lot of livestock products, then your water footprint is large. Production circumstances, they are very relevant for developing countries. Climate is, of course, an important factor, but you can't do change much about that. So it's about evaporative demand. But also agricultural practice is very important. So the water use efficiency of, especially agriculture. This also means that some countries depend on water elsewhere. Most of Europe, Northern Africa, the Middle East, Japan, and Mexico, they depend on virgin water import, so water that is available elsewhere. We talked about farmers, and that most of the water was used in agriculture. We talked about consumers, but I now want to focus a bit more on companies, because also companies have a role here. Water and water use, water consumption of business became relevant issue for especially the large multinational companies, say 20 years ago. Sustainability assessments and sustainability reporting were very much focused on decreasing greenhouse gas emissions, decreasing material use, but then also water became important for companies. Around 2008, we established a water footprint network. And one of the first participants of this network, because they thought it was really, really important, was the Coca-Cola company. And Coca-Cola wanted to be the founder, one of the founders of this water footprint network, but instead it became the first business that was in this network. They find water for the beverage industry really, really important. And this, of course, has to do with the availability of water for their operations. And when they want to open or build a new plant somewhere, then it means that they need to rely on locally produced sugar. And very often this needs to be irrigated, for example, in India. And if there is no water for their plant in the neighborhood, then it's not possible to do the operations over there. So they decided that this is important for their company, so they wanted to do more. We made many, many assessments for different companies, and what you see then is that, and this is of course very logic, that the operational water footprint, so the water that they need in a specific plant, is far smaller than the water they need in the supply chain. So it is very relevant that a company knows where the virtual water of their ingredients for a specific product is coming from. And that they also need to be aware of the importance of their supply chain. As mentioned before, one of the first contributors to the water footprint network was the Coca-Cola company, and then of course they also wanted to have an assessment of their cola. So we did that for Coca-Cola. A small bottle of Coke requires 53 liters of water in total. But it doesn't have to do with the water in the bottle, so the cola itself, but most of the water was needed for the production of the sugar. Yeah? So it's the water in the supply chain that's most important. And if you cannot produce your sugar, then you don't have cola. Okay, then we come to the final conclusions of this presentation. It is possible to save water to trade. If you know where your virtual water is coming from, then water scarce countries can import virtual water as a source of water. If you don't have the water yourself, then you try to produce your products elsewhere in countries that do have water. This also means that the trade of products from agricultural sources reduces water use in agriculture. So it depends where your products are grown, and then you can increase the efficiency of the global water supply system. This means that the export from water-scarce nations can best focus on products with high water productivity. So as much valid added as possible. So as much money here in euros, but can also be dollars, per cubic meters of water. And this is, for example, something that they apply in a country like Israel. What we also saw from this presentation that there are many countries here in Europe, Northern Africa, the Middle East, that depend on water resources in other parts of the world, and that water has become a geopolitical resource, just like oil. Local consumption can have a global impact. As I showed for the example of the cotton shirt, the consumers cause water impacts all over the world, and they don't pay for it. The Aral Sea is pumped empty because we need the cotton for our cotton shirts. Okay, then I come to my last slide. This is on the website of the Water Footprint Network. You can use this to make your own calculations, how much water you use. There's all kinds of information. There's a list of publications, and you find data on water footprints of different agricultural commodities for all the countries in the world and even per province. For example, here is a footprint calculator, so you can put in your own consumption and arrive at your personal water footprint.